All right, folks, so in this problem we want to solve the system that I've listed here. And in this case, this is a system of three ODEs, each involving three unknown functions. So it's a little bit more complicated as far as the size of the system goes, but in a lot of cases finding the general solution is no more difficult than the 2x2 case. What is of course difficult is when you have repeated eigenvalues. That's where things get a little bit messier. But in this case, we should see that we don't have repeated eigenvalues. So as you can do in number 6, where I ask you to do this on your own, I'm going to go ahead and instead of computing these eigenvalues and eigenvectors by hand, I'm going to ask a computer to do it. So let's go to matrixcalculator.org. Let me pull that up. So here we are, and I'm going to go ahead and enter in this matrix. I guess before I do that, I should say normally when you go to Matrix Calculator, this is the first page that is pulled up, and I'm going to go ahead and click on the link for the Eigenvalues Calculator. And we'll go ahead and enter in our 3x3 matrix that we're dealing with here, where the first row has the entries 3, 2, 2, the second row has the entries 1, 4, 1, and the third row has the entries -2, -4, and -1. And we'll go ahead and I'll click find to find those eigenvalues and eigenvectors. So in this case we see, we've got the eigenvalues 1, 2, 3, and each one of those has their corresponding eigenvectors that we can pick. So notice that here we have, in this case, x3 is free. We would find x2 is 0 and x1 is the opposite of x3, and so we make a choice for x3, and that finishes out giving us that completely dictates the rest of the eigenvector. Likewise, we can do the same thing for lambda equals 2, and we can give its eigenvector, and the same thing for lambda equals 3. So I'm going to pull that information over to our work, and we'll continue working the problem. All right, folks, it's going to be a little bit awkward. As I was doing the recording, my microphone cut out, so I'm going to have to do the narration after the fact, and we'll see how I can do. It's a little bit hard to do it this way. So I just want to reiterate, where did these eigenvalues come from that Matrix Calculator computed? It came from that characteristic equation, which we get by looking at the determinant of A minus lambda I, and that's how we get the three eigenvalues, lambda equals 1, lambda equals 2, and lambda equals 3. So for lambda equals 1, we saw that it had the eigenvector, according to Matrix Calculator, -1, 0, 1. Now, one thing to keep in mind is that there's nothing that says we have to use that exact eigenvector. So for example, we could have used 1, 0, -1 as our eigenvector, or even 11, 0, -11, just so long as when we went to that solution to the vector equation and we found that x3 was free, x2 had to be 0, and x1 had to be minus x3, just so long as we pick a value for x3 and then everything for the rest of the eigenvectors determined, as long as we do that correctly, that'll work as an eigenvector. So anyway, we'll use the vectors they came up with. Lambda 1 we have there. When lambda was equal to 2, we had that our second eigenvector was -2, 1, and 0. Again, I apologize for the awkwardness of this with the voice narration after the fact. And then when lambda is equal to 3, we get that our third eigenvector is 0, -1, and 1, or any other multiple of that. But what's key here is that in solving this system of three equations, 3 ODEs with 3 unknown functions, is that we ended up with 3 distinct eigenvalues. Because of that, we can simply represent our solution, and I should be a little more careful. We had 3 distinct real eigenvalues. Then we can simply represent our solutions component-wise, where each solution is just a eigenvalue as a e to that eigenvalue t plus the plus its associated eigenvector. So you can see what I'm doing there. I'm simply representing it the way we did in the 2x2 case. And that's really as hard as this gets until we either have non-real eigenvalues, which isn't too much harder, or if we have repeated eigenvalues, which is where we have to be a lot more careful in the case where we have repeated eigenvalues. We're not going to try to graph this. The text does do one example that shows you a solution in 3 dimensions, and a trajectory curve in 3 dimensions, but generally that gets very difficult to draw. You could ask a computer system to draw it for you, but even that will get a little bit cluttered. You'd have to use some sort of color scheme. So for this is question 5. For question 6 that I'm asking you to hand in on your own, I'd like you to go ahead and just use the matrix calculator to compute the eigenvalues and their associated eigenvectors. If you want to try it by hand, be my guest, but as we see when you start computing those 3x3 determinants or higher, it does get pretty messy, and I'm more interested in our ability to represent the solution and interpret the solution than in simply solving those characteristic polynomials. All right, folks, that's all I've got for you. Please let me know if you have any questions, and have a good day.